Welcome to The Curious Machine. Today we're taking a deep dive into one of the most mind-bending concepts in the cosmos, wormholes.
Wormholes.
You've definitely seen them in science fiction, right? Offering these amazing shortcuts across vast interstellar distances, maybe even through time.
Absolutely.
But what's the reality behind this incredible idea? Are they just pure fantasy, or could they actually exist?
It's a fantastic question, and one that physicists have really grappled with for decades now.
Yeah.
The fascinating thing is the very fabric of space-time, as we understand it through Einstein's theories, it actually hints at their possibility.
Okay.
So our mission today really is to unpack these cosmic shortcuts, explore the physics that suggests they might be out there, and consider what it would truly take to actually traverse one.
Okay. So let's start with the big problem, the reason we even dream about shortcuts. Space is just incredibly vast.
Mind-bogglingly vast.
And our universe has this fundamental speed limit, doesn't it? The speed of light. It's about 300,000 kilometers per second.
That's the cosmic speed limit.
Which sounds impossibly fast, but what does this really mean when we talk about traveling between stars or even galaxies?
Well, that's the key point. The speed of light isn't just some technological barrier we might overcome someday.
Right.
It seems to be an intrinsic limit woven into, well, space-time itself in our universe. So based on what we know now, we simply cannot exceed it, no matter how advanced we get.
And what does that hard limit mean when you factor in those truly enormous cosmic distances? Can you give us a sense of that scale?
Okay, well, think about this. Light takes about 1.3 seconds to get to our moon.
Okay, very quick.
Yeah, 8.5 minutes to reach the sun, maybe 20 minutes or so to get to Mars, depending on orbits.
Still manageable, sort of.
But here's where it gets really daunting. To reach Proxima Centauri, which is the closest star to us after our sun, light takes 4.5 years.
4.5 years just for light.
Exactly. And that's our closest stellar neighbor. If you want to talk about Andromeda, our nearest major galactic neighbor, we're talking about 2.5 million years for light to get there.
2.5 million years.
Yes. And just think about that time frame. 2.5 million years ago. That's longer than the entire evolutionary history of the Homo genus here on Earth.
That puts it into perspective. That's an astonishing amount of time. And our fastest probes, the spacecraft we've actually sent out, they barely even scratch the surface of light speed, right?
Precisely. Even our fastest ones,
Oh,
like
wow.
the Parker Solar Probe diving towards the sun, they only reach maybe 0.06% of the speed of light, a tiny fraction.
So even being optimistic.
Realistically, yeah, even with future advancements, maybe over thousands of years, we might hope to achieve, let's say, 20, perhaps 30% of light speed.
And even then.
Even then, reaching the nearest exoplanets would still take decades. And intergalactic travel would be simply impossible within any recognizable human timescale.
Huh?
A single lifetime, forget it.
So what does this really mean for, the big dream of humanity becoming an intergalactic civilization, or maybe even just exploring nearby star systems in a meaningful way? It sounds like we're fundamentally stuck in our cosmic neighborhood.
It poses a really profound problem for any species, frankly, hoping to expand beyond its home system. I mean, think about it. If a journey to a nearby galaxy takes hundreds of thousands of years, even at some optimistic, realistic speed, what happens when you finally arrive?
Yeah, what would you find?
The destination could be drastically different. Maybe it's uninhabitable by then.
Yeah.
And the people you left behind on Earth, they might have evolved into an entirely different species. They might have completely forgotten why the mission was even launched.
That's a sobering thought. It really highlights the limitations.
It does.
So, okay, if direct travel is so incredibly limited, this is where things get really intriguing, right? Is there a theoretical workaround, a cheat?
Exactly.
Or are we just stuck with these limitations? And that's where wormholes come into the picture, isn't it? The basic idea isn't about breaking the speed limit.
No, you can't do that locally.
It's about cheating the distance.
Precisely. Wormholes offer a theoretical shortcut. They work by warping the very fabric of space-time itself. Think of an apple. A worm wants to go from one side to the other. It could crawl all the way around the surface.
A long way.
Or it could bore a tunnel straight through the middle. The tunnel is much, much shorter.
Right. Or the classic analogy with a piece of paper. You draw 2 points far apart.
Yeah, I like that one too.
Then you just fold the paper so the points touch. You go straight through the folded space, not across the flat surface.
That's exactly it. You don't exceed the speed of light locally while you're inside the wormhole, but the actual distance you need to travel is dramatically reduced.
And this isn't just, pure sci-fi invention.
No, interestingly, this concept emerges quite naturally from Einstein's general theory of relativity. The math, the equations themselves, they actually allow for these kinds of structures.
Really?
Yeah. They were first described mathematically by Ludwig Flamm way back in 1916, and then later rediscovered by Albert Einstein and Nathan Rosen. That's why you sometimes hear them called Einstein-Rosen bridges.
Einstein, Rose, and Bridges. Okay, so if the math allows for them, why haven't we found any? I mean, what would a wormhole actually look like? How would it physically work?
Well, a fundamental model, the sort of basic idea, would involve a mouth that aggressively warps spacetime. Think about something like a black hole.
Okay, with immense gravity.
Right, bending spacetime so much that not even light can escape once it crosses the event horizon. But for something to actually pass through and come out somewhere else, it would need another mouth.
An exit.
An exit, yes.
Yeah.
And that exit would need to do the opposite. It would need to push everything out.
So if one side pulls everything in like a black hole, what would the other end need to be like to, well, let things emerge?
This is where the concept of a white hole comes in.
Okay.
Theoretically, they're the exact opposites of black holes.
Okay.
Instead of pulling everything in, they would constantly emit matter and radiation that appear incredibly bright.
Have we seen anything like that?
Well, that's the thing. We do see incredibly bright objects in the universe, like quasars, for example.
Right.
But those are powered by matter falling into supermassive black holes at the centers of galaxies, releasing enormous amounts of energy in the process. Their signals, their characteristics, are fundamentally different from what we'd expect from a hypothetical white hole that's just sort of spewing stuff out.
So no direct evidence for white holes.
Despite extensive searches, no. We haven't found anything that matches the theoretical description of white hole.
Okay, so if one side of this wormhole needs a black hole and the other needs a hypothetical white hole that we haven't even found, that seems like a pretty significant knowledge gap already.
It is. It's a major hurdle for that simple model.
And even if they did exist, wouldn't the intense gravity on the black hole side just crush anything trying to pass through anyway? Spaghettification and all that.
That's another critical challenge, absolutely.
Hmm.
Even if these bizarre white hole pairs could somehow form a stable connection, the calculations show something else. The throat of a traditional Einstein-Rosen wormhole, the tunnel connecting the two mouths, it would collapse almost instantly due to the gravitational forces involved, long before anything, even a beam of light, could make it all the way through.
It snaps shut.
Essentially, yes. And you're right about spaghettification, too. Anything approaching the singularity inside a typical black hole would be stretched and ripped apart at the atomic level by those extreme tidal forces.
Doesn't sound pleasant.
Not at all. So yeah, this poses a major, major hurdle for that traditional Einstein-Rosen bridge model being traversable.
So, okay, what does this all mean for making a wormhole that something or someone could actually travel through? A traversable wormhole.
Yeah.
If they collapse so quickly and you get spaghettified, how could anything possibly get through?
Well, to keep a wormhole stable, to prop it open against that gravitational collapse, you'd need something to counteract gravity, something that works against the attractive force we're familiar with.
Something pushing outwards.
Exactly. And this leads us to the concept of exotic matter.
Exotic matter. Okay, that definitely sounds like something straight out of a comic book or, Star Trek. What exactly is it?
Well, fundamentally, it's hypothesized matter that has negative mass or negative energy density.
Negative mass. What does that even mean?
It means it would exhibit a repulsive gravitational force. Instead of pulling things towards it, like normal matter does, it would push things away.
So like anti-gravity.
Essentially, yes. Imagine a hypothetical planet made of this stuff. It wouldn't track moons or asteroids. It would actually repel them. It's flipping gravity completely on its head.
Wow. Okay, so we're talking about something that really radically alters fundamental physics as we know it. Does anything like that even exist in the real universe? Have we found any?
We don't have any concrete evidence of exotic matter existing in, large macroscopic quantities that you could hold or build something with.
Right.
However, and this is where it gets interesting, certain quantum effects do theoretically allow for localized regions of negative energy density in space.
Quantum effects, like
Right.
what?
Like the Casimir effect, for instance. This is a real measured phenomenon where if you place two uncharged metal plates incredibly close together in a vacuum, they actually attract each other slightly.
Okay.
And that attraction happens because the quantum fluctuations in the vacuum field between the plates are slightly suppressed compared to the outside, resulting in a net inward pressure, which corresponds to a region of slightly negative energy density between the plates.
Huh. So tiny pockets of it are possible, theoretically.
Theoretically, yes, on very small scales. And physicists like Stephen Hawking and Kip Thorne explored whether these kinds of quantum effects could potentially be harnessed, perhaps scaled up somehow, to stabilize a wormhole's throat.
To keep it open.
Exactly. Keep it open long enough for light, and maybe even objects with mass, to actually pass through without it collapsing.
Okay, so if this exotic matter could exist and could be used to stabilize them, does that open up the possibility that maybe some natural objects, like the supermassive black holes at the centers of galaxies, could actually be stable wormholes, connecting us to other parts of the universe or maybe even other universes entirely?
It's certainly an astounding possibility to consider. If exotic matter is real and can somehow be applied or exists naturally in the right configuration, then yes, theoretically, these incredibly massive gravitational wells could potentially be portals.
But there was that issue with the white hole end, wasn't there? And the one-way trip.
Right, that's a significant point about the classic Einstein-Rosen bridge model connecting a black hole and a white hole. As we discussed, that type seems inherently one way. You can fall into the black hole end.
But you can't come back out the white hole end, or rather, you couldn't enter the white hole to come back.
Exactly. It doesn't allow for a return journey through the same portal.
So no easy round trips with that model.
Not with that specific one. But this is where the work by Kip Thorne and his students, including Mike Morris back in the 1980s, becomes really important.
Oh, okay.
They actually developed a different theoretical model for a traversable wormhole. And this model relies entirely on exotic matter to create and sustain the wormhole's structure.
So it doesn't need the black hole white hole pair.
Correct. It bypasses the need for a white hole altogether, and crucially, their model potentially allows for two-way travel.
Ah, that's a huge difference. That sounds like a potential game changer, theoretically speaking.
It really was. So the theoretical possibilities, yes. It showed that if you had exotic matter, you could potentially design a wormhole that functions more like the shortcuts we see in sci-fi.
And speaking of these really mind-bending concepts, how does this idea of wormholes, these Einstein-Rosen bridges, connect with other cutting-edge physics ideas we've talked about before, like quantum entanglement?
Ah, yes. This is truly fascinating, and where things get even stranger, if that's possible.
Stranger than exotic matter.
Perhaps. There's a really profound conjecture in physics called ER-EPR. It was proposed by Juan Maldacena and Leonard Susskind.
ER-EPR. What does that stand for?
ER stands for Einstein-Rosen bridges, wormholes. And EPR stands for Einstein-Podolsky-Rosen, which refers to the famous thought experiment about quantum entanglement.
Okay.
The conjecture proposes that these two seemingly very different concepts, wormholes and quantum entanglement, might actually be fundamentally equivalent, two sides of the same coin.
Wow. Equivalent. How?
It suggests that when two particles are quantumly entangled, meaning their fates are linked no matter how far apart they are.
The spooky action at a distance Einstein disliked.
Exactly that. The idea is that these entangled particles might actually be connected by a microscopic wormhole, an Einstein-Rosen bridge.
So the instantaneous connection isn't breaking the speed of light, it's going through a tiny shortcut.
That's the radical idea. It's not just a theoretical curiosity. It's one of the deepest ideas currently connecting gravity, wormholes, and quantum mechanics, entanglement. It even suggests that space-time itself, the very fabric of reality, might emerge from the entanglement of quantum bits.
That completely changes how you think about space and time.
It really does. If true, it fundamentally reshapes our understanding of reality.
And what about the quantum foam idea we've discussed, the sort of bubbling energy at the smallest scales? Does that tie into this grand picture as well?
It certainly could. If we connect these ideas, the concept of quantum foam suggests that at the incredibly tiny Planck scale, that's the smallest theoretical size in the universe, where quantum gravity effects are expected to rule.
Right.
Space-time isn't smooth. It's a chaotic, bubbling, fluctuating soup. And within this foam, tiny virtual wormholes could be constantly popping into and out of existence.
Micro wormholes everywhere all the time.
Potentially, yes. And some theories, like string theory, even propose that certain fundamental strings could have negative mass or tension, which might naturally create these micro wormholes.
Oh, okay.
Now, what's compelling to consider is this. If these microscopic wormholes existed in the incredibly hot, dense early universe, maybe the period of cosmic inflation, that rapid expansion right after the Big Bang, could have stretched some of them out.
Inflated them.
Exactly. stretched them from the quantum scale up to macroscopic sizes, the kind of traversable wormholes we're imagining today. It's a pathway, at least theoretically, for how they might form naturally.
That's quite a thought. So, okay, let's assume for a moment that traversable wormholes do exist or could be made. What are the practical hurdles beyond just, finding or creating the exotic matter needed? You can't just stumble into one and hope for the best, right?
That's a crucial point. Absolutely not. For a wormhole to be truly useful for, say, interstellar travel, we'd need to control where the other end leads.
Right, the exit point.
Imagine jumping into a wormhole you found, only to emerge in the middle of a vast, empty expanse of intergalactic space, millions of light years from anywhere interesting. Not very helpful.
No, definitely not.
So we'd need incredibly advanced technologies, maybe technologies far beyond our current conception, uber technologies, perhaps to somehow manipulate or move the mouths of these wormholes to desired locations, like placing one end near Earth and the other near, say, Proxima Centauri b.
But moving a wormhole mouth,
Okay.
wouldn't that itself take a really long time, even if you could somehow just, I don't know, pick it up and move it?
Yes, that's another huge practical challenge. Even if we figured out how to move a wormhole mouth, the process of moving it across interstellar space would still be limited by the speed of light.
Ah, right. Can't break that limit.
Exactly. So it could still take hundreds of thousands or even millions of years just to get the exit end of the wormhole positioned where we want it.
So you spend millennia setting up the express lane.
Precisely. But of course, once it is in place, the journey through the wormhole itself would be incredibly fast, potentially near instantaneous from the traveler's perspective. It really makes you pause and think about the sheer audacity, the time scale of any truly interstellar ambitions.
Yeah.
We're talking about projects potentially lasting longer than our species has existed just to set up the infrastructure. It's also worth noting, while we usually think of wormholes as shortcuts.
They don't have to be shorter mathematically.
Correct. Theoretically, a wormhole could be configured to be long and winding, potentially even representing a longer path through space-time than the direct route through normal space. Though, obviously, the practical interest usually lies in finding or creating ones that dramatically shorten distances.
Okay, this brings us to maybe the ultimate mind bender.
Yeah.
If wormholes can bend space like this,
Mhm.
can they also bend time? Could they actually be time machines?
This is where the theoretical possibilities get truly profound and also deeply problematic for causality. But yes, in theory, if you have a stable, traversable wormhole, you could potentially use it to travel through time.
How would that work?
The basic idea involves manipulating the two mouths of the wormhole relative to each other. You could, for instance, take one mouth and accelerate it to a very high velocity, close to the speed of light, for some time, and then bring it back.
Okay.
Or, alternatively, you could place one mouth in a very strong gravitational field, like near a neutron star or a black hole, while keeping the other mouth stationary in weaker gravity.
And because of time dilation.
Exactly. Due to the effects of time dilation described by relativity, time would pass more slowly for the moving mouth, or the mouth in the strong gravitational field, compared to the stationary mouth.
So one end would be effectively younger than the other.
Precisely. There would be a time difference between the two ends.
So if I then entered the younger end, I'd come out the older end, but at a point in time that's actually in the past relative to the clock at the stationary end. Is that right?
That's the theoretical outcome, yes.
Yeah.
You would effectively arrive at an earlier time in the stationary end's history relative to when you entered the younger end. You could step out and potentially meet your earlier self, or at least exist in an earlier time period.
Wow. That's quite something.
It is. But there's a very significant catch, a built-in limitation according to the physics.
Okay.
You could only travel back in time to the point at which the wormhole time machine was first created or made traversable. You couldn't use it to go back and, say, visit the dinosaurs or witness historical events that occurred before the wormhole existed.
Ah, okay. So no going back before the machine was built. That limits things somewhat.
It does, but it doesn't eliminate the paradoxes.
Right. That immediately makes me think of all those classic time travel paradoxes. The most famous one being the grandfather paradox.
Ah, yes, the grandfather paradox. What happens if you go back and prevent your own grandparents from meeting, thus preventing your own birth? How could you have existed to go back in the first place?
Exactly. How do physicists grapple with those kinds of causal loops?
Well, these are incredibly complex issues, and frankly, they push the boundaries of known physics. There are various theoretical ideas about how causality might be protected. Perhaps there are physical laws we don't yet understand that would prevent paradoxes. Or maybe something like the Novikov self-consistency principle applies, which essentially states that the universe would conspire to prevent paradoxes from occurring. You might try to change the past, but something would always stop you.
Or maybe parallel universes.
That's another possibility, often linked to the many worlds interpretation of quantum mechanics. Perhaps traveling back in time actually shunts you into a parallel timeline, so any changes you make only affect that alternate universe, not your original one. But honestly, these are really deep dives for another day. The key takeaway is that even if time travel via wormholes is theoretically possible according to the equations, it's incredibly complex, potentially requires physics we don't have, like exotic matter, and is still subject to fundamental laws that might prevent or resolve paradoxes. It's not like hopping in a DeLorean.
Right. Not quite so simple. So wrapping this up, while these wormholes remain firmly in the realm of, well, theory and science fiction for now, it's clear they're a truly colossal concept.
Absolutely.
They really push the boundaries of our understanding of physics, of space-time itself, and they offer this tantalizing, maybe distant glimpse into a future where interstellar travel might be more than just a dream on paper.
They are remarkably consistent with the equations of general relativity, which is compelling.
Hmm.
But as we've stressed, their actual existence, especially in a traversable form, seems to rely on these hypothetical concepts like exotic matter or perhaps specific quantum conditions.
Things we have no direct proof of yet.
Exactly. No direct evidence for macroscopic exotic matter anyway. Yet the sheer possibility that these cosmic shortcuts could exist, maybe even form naturally from inflated quantum foam in the early universe, is what keeps physicists absolutely fascinated. The core insight here, I think, isn't just that wormholes are hard to find or build.
Yeah.
It's that their very possibility challenges our most fundamental understanding of energy, gravity, and causality. They force us to confront the absolute limits of physics as we know it.
That's a powerful way to put it. So maybe a final thought to leave our listeners with. If traversable wormholes are truly possible, even if incredibly difficult to make or find, what does that imply about the universe around us? Could advanced civilizations, if they exist, already be using them? Not just to pop over for a visit, perhaps, but maybe to connect vast, otherwise isolated parts of the cosmos, creating a sort of hidden galactic network.
Hmm. That's a fascinating question to ponder, isn't it? A silent, invisible, cosmic subway system. It certainly changes how you might think about the Fermi paradox. Thank you very much for sharing this enjoyable conversation with us. Until we meet again tomorrow with a brand new topic, take very good care of yourselves. Goodbye.